Hey there, physics explorers. Let me start with something simple. Have you ever dropped two stones into a pond at the same time? You see ripples moving outward, right? But when those ripples meet, do they stop? Nope. They combine, sometimes making a bigger ripple, sometimes cancelling each other out. That's exactly what we call the principle of superposition, nature's way of saying when two waves meet, they simply add up. If one wave lifts the particle upward and the other pulls it downward, the particle just takes the net effect, a neat little addition of displacements. Mathematically, it's super simple. The total displacement, y, equals y1 plus y2. And the coolest part? Each wave behaves as if the other one doesn't even exist. They overlap, interact for a moment, and then go on their merry way. Let us say we have two waves moving along the same direction. First wave, y1 equals a 1 sine of kx minus omega t. Second wave, y2 equals a 2 sine of kx minus omega t plus phi. When they overlap, the total displacement becomes y equals y1 plus y2 equals a sine of kx minus omega t plus theta. Here, the amplitude of the resultant wave A is equal to the square root of A1 squared plus A2 squared plus 2A1 A2 cosine phi. Now the phase angle theta tells us how the resulting wave is shifted. Tangent theta equals A2 sine phi divided by A1 plus A2 cosine phi. When phi equals 0, the waves are in perfect synchronization, both crests and troughs align, giving the maximum possible amplitude. Now comes the fun part, what happens after waves meet? If both waves are in phase, meaning crest meets crest, we get constructive interference. The resultant amplitude becomes A1 plus A2 and the sound or light becomes louder or brighter. If they are completely out of phase, when a crest meets a trough, this is called destructive interference. In this case, the amplitude becomes the absolute value of A1 minus A2 and it can even become 0. This is why, when two tuning forks of the same pitch vibrate together, you may hear the sound becoming alternately louder and softer, a clear demonstration of interference in action. The intensity of any wave is proportional to the square of its amplitude. Therefore, these changes in amplitude lead to noticeable variations in loudness or brightness. But hold on, does superposition work everywhere? Not quite. It only works perfectly under some strict physics conditions. First, the medium should be linear and homogeneous, meaning it behaves predictably and uniformly. Second, the amplitudes should be small. If the waves are too large, the medium deforms and linearity breaks. Third, the two waves must have equal frequencies and a constant phase difference. That's what we call coherence. When coherence is missing and frequencies differ slightly, you get beats, rhythmic fluctuations in sound intensity. So next time you hear that wow wow effect when two guitars are slightly out of tune, remember, that's physics playing music through superposition. Let's move to the mathematical core of superposition, the derivation of the resultant amplitude. We begin with two waves, y1 equals a 1 sine of kx minus omega t and y2 equals a 2 sine of kx minus omega t plus phi. Adding them together, we get y equals a 1 sine alpha plus a 2 sine of alpha plus phi. Now, using the trigonometric identity, sine of alpha plus phi equals sine alpha cosine phi plus cosine alpha sine phi. Substituting this into the equation, we obtain y equals a 1 plus a 2 cosine phi times sine alpha plus a 2 sine phi times cosine alpha. This expression can be rewritten in the form a sine of alpha plus theta, where a squared equals a 1 squared plus a2 squared plus 2a1 a2 cosine phi. This is the final result. It shows that the resultant amplitude depends on the phase difference phi. When phi equals 0, the amplitude is maximum. When phi equals pi, the amplitude is minimum. So where do we actually see this magic of waves in action? Everywhere. In sound, when two slightly different notes interfere, we hear beats. In light, we get interference fringes, the bright and dark bands in Young's double-slit experiment. In water, overlapping ripples create beautiful standing patterns of crests and troughs. Even in electromagnetic waves, superposition explains diffraction and polarization. And yes, your noise-cancelling headphones use the exact same principle. They produce sound waves that destructively interfere with unwanted noise, cancelling it out. Let's wrap this up like a physicist. The principle of superposition tells us that when waves meet, their total displacement is the sum of their individual displacements. The resultant amplitude depends on the phase difference, constructive when in phase, destructive when out of phase. Coherence ensures stable interference, and intensity variations explain beats and patterns in sound and light. From ripples in a pond to the colors in soap bubbles, from acoustics to quantum mechanics, this one principle runs the show behind every wave interaction. And that's the beauty of physics. Two simple waves meet, and suddenly the universe gets more interesting. I hope this session helped you interfere constructively with knowledge today. See you in the next concept, where we'll uncover more hidden harmonies of waves.